right, we're going to work through our group work from section 12.6, looking at traces. We're going to take some MRIs of a few different solution sets, starting with z equals 2x squared plus y squared. And so here, we could choose to set z equal to constant, x equal to some constants, y equal to some constants. We'll be able to get there either way. Just to pick something, maybe I'll pick y. And let's choose some constants for y. And so let's start with y equals 0. Then the equation we end up with is z equals 2x squared plus 0. And so in the xz plane, this trace is a parabola. Connects with the origin there. There it is. Let's see if we do y equals 1 now. What trace do we get? We're going to get z equals 2x squared plus 1 squared, which is 1. And so we're going to see a similar picture. Now our parabola is going to be pushed up by 1. Something like that. If we bump y up by another unit, we get y equals 2. The equation we get is 2x squared plus 4. And so we're going to again get this parabola in the xz plane, but now pushed up even higher. And we can see if we keep cranking up the y, this parabola is just going to keep getting pushed up. This actually gives us some nice carryover to negative y's as well. If we plugged in y equals -1, then we're going to get this exact same equation because our y is squared. And similarly, if we plug in y equals -2, we'll get our exact same equation. So we actually have 5 different traces here. We can put these together. All right, so looking at our first one, y equals 0, the xz plane here. So here we have our parabola, looks kind of like that. Y equals 1 gets pushed up by 1, so y equals 1. Our parabola is pushed up by 1, so something like this. And that's the same if we were at -1 for y. We'll have like that going on. And at y equals 2, we have an even higher parabola, and similarly back here at -2, we have our even higher parabola. And so kind of putting this together, we see we have this sort of shape like this. In 3 space, and so what we get, I think this is an elliptical paraboloid. Let me double check myself on that. Yes, that is what we call it. All right, so something like that. All right, our next equation here, z equals 4 minus y squared. And so here, once again, we could choose either variable, z, y, or in fact x, even though we don't see it. And I claim that the fact that there is no x involved in this equation, this is actually a really nice observation to make. This brings us back to even our very first day looking at 12.1, right? If we saw that if an equation doesn't involve a variable, we can draw this in 2 space first and then extend out into 3 dimensions. And so let's do that. Maybe from this trace's point of view though, let's just see what we would get, right? If we chose the x equals 0 trace of our equation, well, there's no x, so we'd get the exact same thing. What about the x equals 1 trace? and we'll get the exact same equation because there's no x involved. Similarly, no matter what x we choose, we're going to get this exact same equation. So let's figure out what this looks like in 2 space and then extend in the x direction. All right, so graphing this in the YZ plane, this looks like a downward facing parabola. It connects the z-axis at 4 and then drops down. So we can take that and bring that into 3 space and then extend in the x direction. All right, so the YZ plane, our parabola looks like this. And we're going to take this parabola and we're going to extend it in the x direction positively and in the x direction negatively. As we do that, we get this kind of cylindrical shape here. This infinite hill, if you'd like. And again, visually we can see how that if no matter what x equals constant that we pick, whether it's x equals 0 or x equals 5 or x equals -10, we're always going to cut through this and get the exact same trace, specifically what we saw over here. So this doesn't have a name as one of our 6 basic shapes for quadratic surfaces because of the fact that we were missing a variable, and so this is more of a parabolic cylinder. All right, for our third equation, I think that the cleanest variable to think about here, so that we don't have to think about hyperbolas, is to set y equal to certain constants. So let's think about that. If we set y equal to 0, equation we get x squared plus z squared equals 1. In the xz plane, this is the unit circle. We set y equal to 1. Equation we get is 1 plus 1 on the right hand side, so 2. And so again we get a circle, but it'll be a little bit bigger. Y equals 2. Similarly, once we cut with that, we'll get 1 plus 2 squared, so 5. And so again, we get a circle in the YZ plane, but it's a little bit bigger than our other 2. And again, some nice mileage out of these computations. Since the y is squared, the equation we get from y equals 1 is the exact same as we would get from y equals -1. Similarly, y equals -2 would give us this same equation here. So we actually have 5 traces here, and we can see what they look like put together in 3 space. All right, so our first one, y equals 0 in the xz plane, looks something like this. Got a little perspective going on. And then if we step out y equals 1, get a little bit bigger circle. And then stepping out again, y equals 2, get an even bigger circle. And then similarly, if we step out to -1, the y direction, I get a little bit bigger circle. And step out to -2, get an even bigger circle, so something like this. And right, if we keep moving out in the y direction, these circles are going to keep getting bigger and bigger and bigger. And if we move in the negative direction, it's going to keep getting bigger and bigger. And so putting this together, we get this sort of shape here for our surface. It's kind of infinite tube that's extending and growing on either side as we move in the y direction. And so here what we get is a hyperboloid of one sheet. All right. All right, moving on, we have some follow-up questions. We are asked, why is the solution set in number 2 of a different nature than those in 1 and 3? So here I have the equations, and really what gave us somehow a different nature is that our equation from problem 2 was missing a variable. Right, so this only used 2 of our variables, and so that's what allowed us to take just one of our traces and extend it just the exact same in the x direction. Whereas over here, things change depending on what trace we took, because these involve all 3 variables. All right, what is the z equals 1 trace in our equation from problem 2? Let's first use our sketch to check it out, and then check it out algebraically. So if we come up to our sketch, z equals 1. Imagine the xy plane pushed up by 1. All right, so we're going to have a plane that goes something like this. And notice that if we chop through this infinite hill with a plane, we're going to cut through our hill in one line over here on this side, and then the other line over here on this side. I'm going to cut through twice on these 2 different lines. And so if you imagine, so looking down on that from above, we'd have the x-axis going to the right and the y-axis going up. Let's draw a picture of that. And it would look like this. And then down here, this would be the other side that we cut through. And algebraically, why does this happen? Well, if we take our equation here and set z equal to 1, right, we get 1 equals 4 minus y squared. So if we add the y squared, subtract the 1, we get y squared equals 3, or y is plus or minus root 3. All right. In other words, y is root 3, or y is negative root 3. And so here, the y equals root 3. In the xy plane, that solution set is actually a horizontal line, right, that we see here. And similarly down here, y equals negative root 3. That solution set is a horizontal line. And so here, from these 2 possibilities, we get these 2 horizontal lines from our trace. All right, so next we're thinking about planes. Let's say we have a linear equation. What sorts of shapes will we get when we take traces of it? Start off thinking geometrically. If we just toss some plane onto the page, well, you can imagine if we took other traces of this plane, each trace we're cutting this with another plane, and however we do that, we're going to intersect at a line, right? So as for example, maybe we trace, we cut with the, if we cut with x equals 0, so the yz plane, then we'd see something like this going on. Right, and if we pushed the x equals 0 to x equals -1 or +2, we get a line. It just might be moved along our plane. And similarly, if we maybe chose y equal to 0, or y equal to some constant, and we started cutting through our blue plane here, we'd again get lines depending on what constant we chose. But however we cut up this plane with cross sections, we're going to get lines as the cross section. Just a real quick, algebraic check on this. If we took, something like 2x minus y plus z equals 4, and let's say if we set x equal to some constant, let's just say 10, then the equation we get, right, is 2 times 10 minus y plus z equals 4. And right away we can just stop. This is a linear equation in 2 variables. And so this is going to give us a line. And in fact, this is really the general argument. If we have a linear equation in 3 variables and we plug in, for one of our variables, well then suddenly our linear equation in 3 variables becomes a linear equation in 2 variables. So we'll get a line as our trace. That's it for today. See you next time.